Okay, so anyway, so like I said, we're gonna look at Markowitz model, and then we're gonna look at what two funded and one funded, and then we're gonna do examples, and then we can move on to CAPM. So in terms of Markowitz model, is that we are trying to optimize so that we can minimize our risk. So we are trying to minimize our risk. So this is our function. So our function will be to minimize our risk. In some textbook, they use 1/2, although they have 1/2 actually, and this is what you use in your lecture. Actually, you use 1/2, 1/2. The sum of I, j, weight of I, weight of j, sigma I. So this is our function of variance, right? So we are trying to minimize this. This is what we are trying to minimize. So in some textbook, they don't put the 1/2. So, but then I saw in the article of Markowitz, he has 1/2, although I don't know where that 1/2 went to when when he moved it. But anyway, this is how you should write it because this is how they teach you in class. So this thing will have our constraint in this case is going to be our return, the function of return. We know that the function of return is going to be the weight portfolio, and the sum of the weight needs to be equals to 1. So in Lagrange equation, so remember we are trying to optimize. So to write our Lagrange equation, so our Lagrange is going to be what? It's going to be the sum 1/2, the sum of I, j, weight of I, weight of j, sigma I, and sigma j, minus the sum of our weight returns minus portfolio returns, right? So basically here, so they will tell you what is the desired portfolio, like the desired portfolio returns. So I just have to like throw this thing out there. So anyway, your minimum variance for a specific portfolio return. So you have a return. So you specify a return, right? Like you have your own returns that you want. And then you're trying to find the minimum variance of that return. So I think this is why I had this thing of phase available set over here. So I remember that from your book, this was the feasible set of a risky asset. So all risky assets. This one is when you have more than 2. So it will look like something like this. So if this is your return, so let's say this is RP star, you trying to find the one which is over here, the one which is at the efficient frontier. So this is the one you are trying to find. Any other one, like any other returns, you can see that you will still have the same return, but it will have a higher risk. You are trying to minimize the risk. So this is what, okay, so this is why you use Markowitz models. You have your own specified return and you're trying to minimize the risk, hence this equation. So how do you minimize this risk? Is that you are going to find the derivative the first derivative. I'm going to say the first derivative of weight of I of L, and then you equate it to 0. Then you find again the derivative in terms of lambda. This thing lambda, yes, equals to L, and then again you're going to find the partial first derivative terms of mu, like of L, and then you're going to equate it to 0. So this first equation over here, it will give you something like this. It will give you something like this. It will give you the sum of all the J asset, like returns. So this is portfolio variance, covariance minus mu, the sum of I. Okay. Yes, minus mu. So that thing is lambda. So this is for all i's. This is for all your i's, and then you do the same for this one. So this one again for lambda. So lambda will basically give you the sum of all the weight, the returns. It's going to be equals to portfolio return, your own desired portfolio return, or the stated portfolio return. And then when you derive the the Lagrange in terms of mu, you will be left with the weight equals to 1. Sorry about my W's, they're so ugly. W. So so basically you will have n 1 1. So you will have n plus 2 functions, right? So to like prove it, so you can write this thing as a matrix form in order to solve it simply. So basically it will be the weight of 1 1 up, like the cover of returns of 1 and the return of 1, and then you're going to have the covariance of returns of 1 and the returns of n minus r1 minus 1 all the way to the covariance of the returns of n and 1 all the way to the covariance of the returns of n minus the returns of n minus 1, and then you're going to have the returns of n of 1 all the way to the returns of n. Then you're going to have 0 0, then you're going to have 1 1 0 0. So this is how you can simplify it. Weight 1, weight n, lambda, and mu. Zero up to 0. The returns, your desired portfolio return. There you have it. So basically this is like a x equals to b. So when you use your Excel, you basically going to say your x is going to be equals to, solve it like this. So anyway, I have an example over here. So I'm not going to spend a lot of time doing the example, but I just want to show you how to answer these questions. So for this one, this is what I would do. Make space. So this question says that consider 3 assets which have their returns, for which their returns have the following covariance matrix and the mean value vector. So this one is the mean value vector. This one is the covariance matrix. So they want you to find the minimum variance portfolio, which has returns of 17%. So how do you do this? So when you solve this, so you are basically going to take this thing over here, like this equation. So when they ask you a question like this, there is no need for you to like prove this thing. So you just have to like know this matrix, and then you can like solve it. So basically what you will have is sometimes there's going to be 0.5, 0, 0.1. So the returns, the negative returns of 0.2 minus 1, 0, 0.4, 0, negative 0.15, negative 1, 0.1, 0, 0.5, negative 0.2, minus 1. Then you're going to have 0.2, 0.15, 0.2, 0, 0. Then you're going to have 1, 1, 1, 0, 0. I can like simplify it further, and then I can say it's going to be 0, 0, 0. The returns, which is going to be 17%, so it's 0.17. And then 1. And then you're gonna reduce your matrix, and then you're gonna find your answers. So I've done this earlier on. I reduced them, and then what I got, although I am not very confident with these answers, I think I made a mistake somewhere. But then what I have is something like this. So the mu is gonna be 888 over 5, 845. And lambda is gonna be 27 over 16700. And the weight, again, after I have normalized them, I got 0.8578 for 1 and for 3, and then for 2, 0.42844. So you can try this at home, and then you can check if it's correct. But then I will do this thing later on. Or you can actually use your computer, like your Excel. I think if they normally want to ask a question as big as this one, what happened to my screen? Okay, if they want to ask you a question which is this big, they normally would ask you in Excel. The one they would ask you like this. I am going to show you now. So what if you are not given the returns? Like, what if they do not specify what returns you should have, right? In this case, okay,
right. So this type of question wouldn't necessarily be asked in a written exam. If they ask a question like this, it would be in the Excel one.
Normally, because it will take time to like prove it.
Okay, cool. Thank you.
Yeah. I think froze. Sorry. Okay, so yeah, they can ask you, but then because it's too long, they'll have to like give you more marks. But because there are many chapters to test, I'm like to test on to so they would rather opt for the following option. So they would rather not tell you the returns, right? Then they can ask you to say find the minimum variance normally. So they can just say find the minimum variance. They ask you to find the minimum variance. So from that equation, the of W in terms of I equals to 0. So basically you have you have something like this. You have the sum of all the j's, the weight of j, the covariance of I and j, minus lambda times of I minus mu equals to 0. So if they, so something like this, they can ask something like this. So if they do this and they say find the minimum variance. So the minimum variance is when your mu is going to be equals to 0 and your lambda is going to be equals to 1. And then so if this, so if this is the case, you're basically going to have your covariance matrix as they said there. So you're going to have 0, 5, 0, 1, no 0. So it's going to be 0, 0, 1, 0, 1, 0, 0, 4, 0, 4, 0, 0, 1, 0, and 0, 5. So you are basically going to have your covariance matrix 1, 1, 1, and then you're gonna solve this because your mu is gonna be equals to 0 over here. So in essence, this thing's gonna be like this. It's gonna be sigma 1, 1 up to sigma 1 n all the way to sigma n1 to sigma n plus to 1, 1, 1.
So sorry, why is it the 1, 1, 1?
Because again, because you have mu only, so you are basically going to, again, so your mu's are going to be ones. So when they go to the other side, it's going to be positive. So you will have positive 1 for every equation.
Is it because you use lambda 0 and mu 1 and then they become
Yes,
1,
yes.
1?
Yes.
Okay, cool. Thank you.
Yeah. And then they would again ask you to find, or they can just, and then this, yeah, but then this one is the most common one. Or they can just basically ask you to find any other efficient portfolio. If this is the case, you are going to let your mu equals to 1 and your lambda equals to 0. So your matrix is going to be something like this, going to be mu 1, 1 up to mu 1 n. I mean like sigma n1, sigma nn equals to the returns. So if this thing is going to be 1, you will be left with the returns of each asset. So you'll be left with the returns of 1 up to the returns of n. So these are the expected returns. So, and then you're going to solve this matrix. So anyway, we have learned that in Markowitz model, let's say maybe you have like 50 assets. It simply means that you will have to take into consideration all the risk of this asset, all the return, and the covariance as well. And it might take you time to find those values. So in order to avoid the hard work, in order to avoid the hard work, you can use a method called, or a theorem called a two-fund theorem. In this two-fund, so in this theorem, instead of like basically buying all the assets, you can basically just find 2 assets which lies on the efficient frontier, and then you buy them to build your own desired portfolio. So if you are on the thing over here, so you have an asset over there. So this is still your efficient frontier, and then you have another asset over there. So if this is the case, and then you want a asset which lies here, maybe this is what you want. So instead of buying all the assets, instead of buying all these assets, you can just buy this 2. You can just buy buy these two funds. So these two funds. So let's say maybe this one is fund 1, it's fund 2. So you can just basically buy fund 1 and fund 2. So and then you can find your returns. Sorry, I'm coming. Yeah, so basically, because you have two funds, you can simplify this back to your chapter 1. I think it was section 102, where you can see that the returns. So this one's going to be the returns of your portfolio. So it's going to be RP. Going to be equals to the returns of let's say maybe alpha is going to be the weight of 1, weight of fund 1, right? So if this is the case, then you can say that alpha returns of fund 1 plus 1 minus alpha returns of fund 2, right? So when you simplify this, and you're gonna find how much of asset 1 should you buy and then how much of asset 2 should you buy, right? So basically your returns are gonna be something like this. You're gonna have, like your weight is gonna be the returns of your portfolio, of your own desired portfolio, minus the returns of asset 2 over fund 1, fund 2. So this is how you use two fund. You can see it's much easier. There's no need for you to even calculate the variance or anything. As long as you know the returns of these two funds, you can basically find how much weight should you invest in fund 1 and in fund 2. When you know how much weight should you invest in fund 1 and fund 2, you will be able to allocate how much should you invest in each asset. So again, does that make sense?
Yeah, it makes sense.
Okay. Okay, there are no questions over here as well. So anyway, so I'm going to continue. I'm going to one fund theorem. Now we have also seen, now we have seen that since we can basically just buy two funds instead of buying all the assets, can we actually simplify this idea further? And yes, we can. And we can make it better, and then we can use it again. So this method is going to be called the one fund theorem. In one fund theorem, you are going to include a risk-free asset. Include risk-free. So for your risk-free asset, so and then you're gonna have one fund, and then you're gonna have one mutual fund. So you include a risk-free asset plus a mutual fund. So let's say maybe this is your risk-free asset. This is your risk-free. This is where it is, different color, right? So this is your thing over there. So to find and let's say maybe your asset is going to be, your fund is going to be somewhere here. If this is the case, then your thing is gonna look like that. So you can see that at this point, like at this point over here, from here to here, this fund is so much better because it gives you higher return than any other of your, than anything on your risky assets. It gives you higher so it gives you a higher return for any given risk. So in order to make it better, you can basically find an asset, so a fund, which we're gonna call your tangent portfolio. So you can basically find a fund such that this line touches it at a tangent, touches the risky feasible set at a tangent. It touches it at a tangent. If this is the case, you can see that investing over here on this feasible set is so much better than any other set on your risky assets, right? So you are better off including a risk-free asset in your portfolio, given that you can also find your tangent portfolio. So in this chapter, we are mostly going to be concerned about finding our tangent portfolio, because remember that we are doing financial engineering, and what we are trying to find is to maximize our returns, right? And minimize our risk. So for any given risk, we want to find the highest possible return. So, and we can find that maximum possible return at that tangent portfolio. In other articles, they say you are maximizing your Sharpe ratio, but in this chapter, like in our course, it's so much better to use the name a tangent portfolio. So when they talk about the tangent portfolio, they talk about this portfolio over here. The one, yeah, so this portfolio over here, it's our tangent portfolio. So how do you find this tangent portfolio? So to prove this thing like takes time. So I'm not gonna do this proof because I don't think they're gonna examine it anyway. But I think if they do, they can take you halfway, and then you can finish it up. So anyway, I'm not gonna do the proof. So to find this tangent, right? So you are trying to maximize your tangent. So basically, you are trying to maximize this thing over here. So how do you find tangent? Is can you find it using the gradient, right? So this point over here, we can just say it has a risk of P and the returns of P. So to find the tangent, you can say the returns of P minus risk-free over, okay, let's just say, okay, yeah. And then you're gonna say variance. So we can use variance instead, variance of P minus the variance of our risk-free rate. So there is no variance for our risk rate, right? So we're just gonna write it like this. And then you simplify it until this equation look like something like this, until it look like this, until it look like risk-free. I mean, like risk of an asset, I mean, like the returns of an asset minus risk-free rate equals to the sum of the covariance matrix. This is gonna be in terms of J times the weight. So this one is gonna be your weight of an asset, or you can just say that it's an unnormalized weight. So this will be your unnormalized weight. So if you have any questions, you can ask them now. So this is basically how you find your tangent portfolio. So in terms of matrix, you can write it like this. I don't want to use this color. So you will have your covariance 1, 1 up to 1n, all the way to n1 up to n, and then you solve for r1 minus rf, r1, I mean like rn minus rf. when you solve this thing, the weight you are, again, the weights you are going to find, these weights, you are going to normalize them, and then that will be the weight of a portfolio of your tangent product portfolio, basically. So it is not that complicated as well. So any questions at the moment? Okay, no question. So here's an example. So it says find the minimum variance portfolio. So to find the minimum variance portfolio, so we're saying that you're gonna have your weight of J, covariance of IJ minus lambda Ri minus mu equals to 0. And then you let mu equals to 0, like lambda equals to 0 and mu equals to 1. If this is the case, this is what you will get. Zero, 5, 0, 0, 1, 0, 0, 4, 0, 0, 1, 0, 0, 5, 5. I think I'm gonna have 1, 1, 1. And then how how do you solve this? You're gonna say R3 is gonna be minus 0, 1 over 0, 5 R1. Then you're gonna have 0, 5, 0, 0, 1, 1, 0, 0, 4, 0, 0, 0. Let me see. Yeah. 0.48. You're gonna have 1 over here. Then you're gonna have 1 over 3. So you can see that the weight is gonna be what it's gonna be. $25 over 36. Do you guys find the same answer? And then for weight of 2, you're gonna have what? You're gonna have 1 over 0.4. Be 5 over 2. And then for weight of sorry, this one is 3, this one is 2, this one is gonna be 1. Do you guys find the same answer, or am I doing something wrong here? So these are the answers I get. Okay, you can already see that these things are not normalized. So you will have to normalize them. So how do you normalize them? So you sum them. You can just say that y0 is going to be equals to the sum of all your weight. And all your weight is going to be equals to what? 25 over 36 plus 5 over 2 plus 30, again, plus 67 over 36. 91 over 18. I don't remember finding this answer last time. But then at least you, again, I'm like, at least you all have an idea of what's happening, right? There's a question over here. None from my side. Neris, I don't understand your question.
Oh no, sorry, sir. That was when you asked if we had questions a while ago, and I just said none from my side. No, I don't have any questions about this.
Oh, okay. So the weight of 1 is going to be equal to what? It's going to be equal to 67 over 36 over 91 over 80. 0.368. You guys can confirm if you find the same answer. So you can do the same for all the weight for 2 and for 3. And then they can ask another question. They can say that find another efficient frontier. So this is when you let mu equals to 1. I mean, like lambda equals to 1 and then mu equals to 0. And then you solve it too. Given the above portfolio, use the two-fan theorem. Okay, and then you're gonna use your two-fan theorem. So let's say maybe, okay, to answer this question, you need to have done both of these questions, right? And then whatever returns you're gonna find, so you're gonna find the weight of asset 1 of your portfolio A. So let's say this one is 1, and then this one is 2. And then you're gonna say your returns. So this one is the portfolio returns that you are looking for. The returns of 2 over returns of 1 minus the returns of 2. So you are basically going to find the returns of both portfolios, and then you're gonna solve it.